Hello, my name is Lucas Christowski, and I'm a professor at the University of British Columbia. I am going to be speaking today about the design of grating-based silicon photonic filters. I will describe silicon photonics fabrication using SciEpic Fab in Canada. I'll introduce waveguide Bragg gratings, operating principles, and in particular a key parameter, which is the grating strength. Then I'll describe how you can spectrally tailor an arbitrary response using layer peeling and phase modulation apodization. Then I'll describe contra-directional couplers, including operation and examples. The devices that I describe in this presentation have been made via Canada's Silicon Photonics Foundry, SciEpic Fab. This is a consortium of over 10 companies and several universities, with funding from the Canadian and Quebec governments. We are involved in improving and developing new processes for silicon photonics. The main tool in SciEpic Fab is a state-of-the-art electron beam lithography tool. It can fabricate on small samples, like 1 centimeter, or up to the industry-standard 200 millimeter wafers. Compared to regular foundries that use deep UV lithography, we can achieve much higher resolution, smaller features, and better overlay accuracy between masks. And since we don't use masks, fabrication turnaround times are much quicker for prototyping. SciEpic Fab can fabricate different types of waveguides. Most of our work has been in silicon so far. We can make thermo-optic phase shifters and defect-mediated detectors. Light can be coupled into the chips using fiber grating couplers on the surface of the chip or edge couplers. Bi-monthly fabrication is available using cost-shared multi-project wafer runs, which are conducted by Applied Nanotools. We have a roadmap of future processes we plan to develop, including expanding the wavelength range to the mid-IR, silicon nitride waveguides, different types of detectors, including for single photons, different modulators, and packaging for optical fibers using photonic wire bonds. We are working towards integrating lasers with silicon photonic chips, and we have a few approaches for integrating electronics. We continue developing open source tools, process design kits, and libraries for various applications including classical and quantum. Let's discuss Bragg gratings. Bragg gratings are useful for making semiconductor lasers. The picture on the right shows the laser developed by UC Santa Barbara and commercialized by Intel. Such a laser needs two mirrors, which can be made by introducing a periodic corrugation on the waveguide to create a Bragg mirror. Bragg gratings have been used to design different types of filters, which can be used for optical communications and microwave signal processing. Here is an example of a wavelength division multiplexed filters. Let's discuss the operating principles for Bragg gratings. The Bragg grating is a wavelength selective filter. It consists of a waveguide with a periodic structure or grating. Light is coupled from the forward propagating mode into the backwards propagating mode. The reflection features a passband response, whereas the transmission features a band reject filter. And the central wavelength is lambda b, the Bragg wavelength. There are many parameters that control the device performance. First, the grating period determines the central wavelength. The widths of the waveguide are designed for the desired wavelength, and the corrugation width, dW, is the change in the waveguide width and determines the bandwidth of the filter. The Bragg grating central wavelength can be found from the phase matching condition. Constructive interference occurs when there is a 2 pi round-trip phase between the light reflecting from the first grating tooth to the second grating tooth. So the Bragg wavelength is found from the optical wavelength inside the waveguide, matching 2 times the period. We can look at this using wave vectors. The grating has a negative vector of 2 pi divided by the period. The propagation of light in the waveguide is beta, and this is 2 pi times the effective index divided by lambda. Light can go forwards or backwards. These 3 vectors can be added, where the right traveling wave vector minus the Bragg grating vector gives us the left traveling wave vector. The result is the Bragg condition, where the Bragg wavelength is 2 times the effective index times the grating period. There is an analytic expression for the grating reflection spectrum. To predict the spectrum, we need a parameter called kappa, the grating coupling coefficient, which can be interpreted as the amount of reflection per unit length. Each grating tooth contributes a tiny reflection, which when added up can lead to nearly 100% reflection. If we know the coupling coefficient and the length of the grating, we can predict the peak reflectivity and also the bandwidth of the grating. An important challenge is to determine kappa either from experiments or simulations. Let's discuss how we find the grating coupling coefficient. We are aiming to make a connection between the physical parameters of the grating, such as delta W, which is the waveguide width variation, and the parameter kappa, which goes into the model. We can do this by measuring the optical spectrum of a grating and finding the delta lambda as shown in the plot, then using the delta lambda expression to extract kappa. This can be done from both experiments and simulations. This plot shows extracted values of kappa from several experiments using different types of waveguides such as strip and rib waveguides and for different fabrication processes. The x-axis is the corrugation width dW, and we see that the larger the teeth, the stronger the grating. We have experimentally compared sinusoidal gratings versus rectangular gratings, and we find that for very large dW values, the rectangular gratings don't behave as we might expect. The sinusoidal gratings surprisingly allow us to obtain larger kappa values and thus larger bandwidths. Also, we see that there is a parasitic effect where the central wavelength changes with increasing dW value. Data from the measurements can be put into a compact model so that circuit designers can simulate circuits. If we want to model a grating, one way is to simulate the entire structure in 3 dimensions using finite difference time domain simulations. These take a really long time for long gratings, so are not practical. An alternative method is to simulate only one unit cell or one period of the grating. If you make the boundary conditions in the simulation periodic, called block boundary conditions, you can effectively simulate an infinitely long grating. From the simulations, you can find the bandwidth, then use the analytic expression to find kappa. This approach is the same that is used to calculate band structures for photonic crystals, except here it is done in 1 dimension. We have compared these simulations to experiments and found excellent agreement. Thus, I recommend using this approach if you would like an accurate prediction of the grating strength. And the link at the top provides some more details to how to accomplish this. Next, I would like to discuss some work with my former student Rui Cheng on designing complex gratings. First, we consider that a grating can be thought of as a finite impulse response filter where the designer control all the filter coefficients, in our case, the phase and the reflection of each grating tooth. This gives us many parameters to adjust to make a filter. Let's start with a uniform grating. The response looks like a sinc function because the grating has a finite length. We can improve the spectrum by introducing a Gaussian window to get rid of the abrupt transition from the waveguide to the grating. This is called apodization, where we change the grating strength kappa along the device and it improves the extinction ratio. Now, what if you were asked to design a specific transfer function? The example shows an amplitude with a passband characteristic featuring a phase transition in the middle. How do we design such a grating? The approach considers that there is a time domain response of the grating coming from the numerous reflections that occur at different points in time. We take the inverse Fourier transform of the spectrum to get the time response. For the ideal target spectrum, we get a non-causal time domain signal, which is also infinite. So we shift it in the time domain and truncate it. Taking the Fourier transform, we get a spectrum that is physically realizable. With the spectrum, we now must find the grating profile, including amplitude and phases along the grating. There is an algorithm called layer peeling, which goes through layer by layer to find the coefficients of each. The algorithm chooses a reflection amplitude and phase for the first reflection, then subtracts it from the spectrum and continues layer by layer. The result is a profile for kappa and phase along the grating. Next, we convert the kappa and phase values into a physical grating structure. The simplest approach is to change the width of the waveguide. This works well for apodization, but there are other methods. This slide shows several different approaches for creating a grating. Changing the waveguide width comes with the parasitic changes in the Bragg wavelength, which introduces unwanted chirp. We can also change the duty cycle or use lateral misalignment, which shifts the top teeth versus the bottom teeth. These two techniques also have the parasitic chirp problem. A very nice approach is to use phase modulation, where only the grating period is changed locally. This technique doesn't have chirp, but it introduces echoes in the optical spectrum. The way phase modulation works is that when you keep the period constant, you have the maximum value of kappa, and when you modulate the period, you reduce the strength of the grating. You can use the map to convert from the desired kappa to a physical structure. There are different modulation functions you can use, such as sinusoidal, square, triangle, or sawtooth. These have different transfer functions, but work on the same principle. The question is, which of these is the best? We compared several modulation functions and found the spectrum for each. We analyzed the spectrum ripples and extinction ratios, and we found that square or sawtooth modulation leads to better optical performance than sinusoidal modulation. Returning to the target transfer function, we can design the grating using several of the approaches we discussed. This slide shows that the phase modulation technique results in the best performance for the Hilbert transformer with this complex spectral shape. Next, let's discuss contra-directional couplers, which are abbreviated as CDCs. The contra-directional coupler is a wavelength selective filter, like a Bragg grating, but with 4 ports instead of 2. It can be used as an optical add-drop multiplexer, where you can design a passband response for the drop port. You can cascade these filters to achieve high extinction ratios and flat top response. Professor Yariv first proposed this device in his optoelectronics textbook, and it has been fabricated in silicon photonics by several groups with different ways of implementing the grating. The contra-directional coupler consists of 2 waveguides with a periodic structure or grating. Light is coupled from the first waveguide backwards into the second waveguide using the grating. The drop port in the second waveguide features a passband response, whereas the through port in the first waveguide features a band reject. You can cascade many of these filters, and each one can have its own central wavelength. Thus, you can build a wavelength division multiplexed system. You can also thermally tune the gratings, and if you have a cascade of 2, then you can tune them relative to one another, thereby achieving a tunable filter. Let's discuss how these filters operate. There are many parameters that control the device performance. First, the grating period determines the central wavelength. The widths of the waveguides are designed for the desired wavelength. The corrugation widths and the gap determine the bandwidth of the filter. First, let's consider the model for a regular waveguide. On the y-axis, we have the optical frequency. The x-axis is the wave vector, which is related to the effective index, and it has been normalized to the grating period, which we will introduce next. The line shows the solution to eigenmode calculations and tells us how fast light travels in the waveguide for a given frequency. If we introduce a periodic structure, we see a reflection of the solution at the k equals 0.5 point. We also see that there is a band gap which opens up. This band gap is exactly the bandwidth that we previously identified and corresponds to wavelengths that are reflected by the grating. Within the band gap, light cannot propagate forward and is reflected. Along the lines, there are solutions for light transmitting through the grating as though it was an ordinary waveguide. Now, if we have 2 parallel waveguides, we get 2 such solutions. We use different width waveguides to separate the solutions. By introducing a grating, we see the same folding and two band gaps appear at the k equals 0.5 point. These correspond to the reflection bands for each of the independent waveguides. But there is a third band, which is the contra-directional band, and it occurs due to the coupling between the two waveguides. We can do band structure simulations similar to regular Bragg gratings and find these band gaps and operating wavelengths. We use the same equations to find kappa. The wave vector diagrams are the same as regular Bragg gratings, except that we now have two different propagation constants, one for each waveguide. This allows us to find the Bragg wavelength from the average of the two effective index values. Here is an optical spectrum of such a filter, showing the main contra-directional band. We also see the reflection occurring in the input waveguide as a notch in the optical spectrum. Let's discuss some design considerations. First, we don't want this to be a regular directional coupler, so we make the two waveguides different. That way, light will not couple forward and across. Second, we want to eliminate the Bragg reflection that occurs in one waveguide. We can do this by offsetting the teeth by 180 degrees, which cancels the individual grating. This approach keeps the contra-directional coupling, since that coupling is strongly affected by the corrugations in the gap region of the coupler. We can use apodization techniques to improve the optical spectrum and get high extinction ratios. Here we show the comparison of uniform grating versus apodized. The insertion loss of one filter is only 0.2 dB. Cascading multiple such filters allows us to improve the extinction ratio, here shown to be over 50 dB. With 4 stages, you get a total insertion loss of only 0.8 dB. Fabrication imperfections affect the spectral response of Bragg grating devices. Specifically, chip non-uniformity leads to variations in the effective index, which leads to a parasitic chirp. There are also random fluctuations. These all degrade the spectral quality. You can make a spiral grating to reduce this fabrication problem. Lithography smoothing effects are a major challenge for designing gratings, particularly if you don't have a predictive model for the fabrication process you are using. Thus, to design a grating using deep UV lithography, you need a minimum of 2 fabrication runs. In the first, you need to either fabricate many gratings and characterize them, or build a lithography prediction model. Then, in the second fabrication run, you can design your system once you know the grating performance. Let's look at a few examples of CDCs. An example application for CDCs is a wavelength division multiplexed filter. Here, there are 4 stages to each filter. This results in outstanding performance, very low loss of less than 1 dB, and a flat transmission band of 6 to 7 nanometers for each channel. Contra-directional couplers can be used for quantum information applications as filters for single photon source generators. With a strong laser, a ring resonator can generate single photons. Then the CDC will be used as a filter to remove the strong pump laser and pass through the single photons. We have implemented a simulation framework using an open source layout tool, K-Layout, and numerical interconnect. It allows us to predict the spectral response of the entire circuit. In a typical Bragg grating design, the component is modeled using eigenmode solvers and finite time domain simulations. Then, a design is created as a layout for fabrication. We have combined all these parts. The user creates a circuit containing contra-directional couplers with different parameters. K-Layout calls the simulation engines to find the optical response of each component in the circuit and builds a library of compact models. Then, a circuit solver, numerical interconnect, uses these compact models to predict the entire circuit response. Here's an example where you can go from a mask layout to a full circuit simulation. This allows you to make sure that you connected waveguides correctly and validate your design before submitting it for fabrication. There are more things you can do to improve the usefulness and performance of Bragg gratings, particularly the very useful contra-directional couplers. Specifically, we can consider more sophisticated apodization, such as phase modulation, and in principle, we could design any spectral filter you want and make it a 4-port device. If you have any specific custom filter requirements, please let me know, as I would be interested in discussing these with you. I end my presentation by sharing some online resources and events relating to silicon photonics training and fabrication. Specifically, the SciEpic program offers an online course where you can design Bragg grating filters, and we will fabricate and test them for you. SciEpic Fab offers multi-project fabrication runs every 2 months, so if you want to fabricate some gratings, we can make them for you. Thank you very much for your attention.